Hi everybody, this is Nageswara, Assistant Professor of Physics, Government Degree College, Chintalapudi. In this presentation, I want to analyze what is spherical aberration, how can we measure spherical aberration at different conditions or different objects. So this is the convex lens, O is the point object. If the rays are incident on the convex lens at a different height, the image formed at different places. Due to this, the images are not a point images. Such aberration is called spherical aberration. We know spherical aberration is a one of the type of monochromatic aberration. So before discussing about the spherical aberration, once again we have to remember what is monochromatic aberration. If the object is single color, that is single color, that is monochromatic light, that is also called simple single wavelength, the image formed by the lens is blurred or at a different sizes at a different positions. This kind of defect is called monochromatic aberration. So the aberrations produced in an image given by the monochromatic light is called monochromatic aberrations. Monochromatic aberrations are five types. One is spherical aberration, second one is coma, third one is astigmatism, fourth one is curvature, and fifth one is distortion. Spherical aberration and coma produces blurring of images. It means that if a point object when we have to take in, the image is not a point image. It is blurred. It is not clear. But in case of astigmatism, curvature and distortion, the image found by the lenses are dislocated. Maybe the point object can see as a straight line, etc. So we have to analyze now spherical aberration. Before that, what is spherical aberration and how can we measure the spherical aberration? We will discuss here. L is a convex lens. Y is the point object placed on the principal axis at some distance. We know even if it's a monochromatic light object, the light rays will move in all directions, in different directions. So one of the ray is incident on the convex lens very nearer to the principal axis. A ray which is passing nearer to the principal axis is called paraxial rays. These paraxial rays formed an image at IP, far from the convex lens. And another ray is incident in the convex lens, far from the principal axis. So this is called marginal ray. So the marginal rays are far from the principal axis. So these rays are formed an image IM nearer to the convex lens. Two images IM and IP are not point images. So this defect is called spherical aberration. So how can we write? The failure of the lens to form a point image of an axial point object is called spherical aberration. So in which there is a convex lens we have to take, a point object is placed on the principal axis. This is the marginal ray whose image is formed at IM nearer to the principal axis. IM is the marginal image nearer to the convex lens. If paraxial rays are nearer to the principal axis, incident on the convex lens and formed an image at IP. IP is the paraxial image. So this kind of lens defect is called spherical aberration. Even this IM and IP are not point images, Those are elaborated or blurring of images. So in case of concave lens, this is the concave lens in which this is the principal axis. If ray is incident on the concave lens, the images are formed at IV and IP. So this is the marginal ray which is incident and the image is formed at IV. This is the marginal image. If paraxial rays is incident on the concave lens, the image is formed at IR. This is paraxial image. In case of a concave lens, the marginal image is right side to the paraxial image. In case of convex lens, the marginal image is left side of the convex lens, just like chromatic aberration. Now, why it is happening? Why this kind of spherical aberration is happening? So now, once again, we want to analyze this. What is paraxial rays? What is marginal rays? So the point object is placed on the principal axis. This is the paraxial rays, which is nearer to the convex lens. If the convex lens is can be assumed as different zones or different circular zones as shown in this diagram. There is the central zone and the second zone, third zone, fourth zone, fifth zone, and etc. The paraxial rays is passing through the second zone. It is nearer to the principal axis. The image is formed at IP. This is the image formed IP which is passing through the second zone. And the marginal rays which is passing through the fifth zone, which is far from the principal axis. And the final image is formed at IM. Why it is happening? The focal length of the convex lens is depending on the radius of the different circular zones. If radius increases of the circular zone or maybe convex lens, the focal length decreases. So in case of marginal rays, the radius is very high. Circular zone radius, fifth zone is very far from the principal axis. So if radius is very high is nothing but whose focal length is very less. So that the image is nearer to the convex lens. In case of paraxial rays, the radius, circular zone radius is very less. So its focal length is very high. The image is far from the convex lens. So due to the focal length changing with the radius of the circular zone, so spherical aberration exists. So why? How? What is the shape of the final images formed? So if a in which the distance between IM and IP paraxial image and marginal image is the measurement of the longitudinal spherical aberration. This is the longitudinal spherical aberration, and this is also called axial spherical aberration. The remaining rays, which is in between marginal rays and paraxial rays, are formed in between IM and IP. Now, if a screen is placed at a normal to the principal axis at IP, this is the axis. That is the screen which is placed normal to the principal axis. The image is not a point image. The central image is this is a circular shape of image. That is like just looks like a circular disc. The image at IP. If the screen is moving from IP to IM, then also the image is circular, just like circular disc. So at IM and IP also the image is not a point image. There is images in the form of circular disc. If the screen is moving from IP to IM at a certain position, that is at AB, The image is circular, but whose radius is very small. The intensity is equally distributed. So this is the nearest approach of the point image. So this AB is called circle of least confusion. So the image of the point object is AB. Now, how can we calculate spherical aberration in case of plane refracting surface? So, for example, this is the AB is the plane refracting surface which is normal to the axis X. So, AB is the plane refracting surface and it is placed perpendicular to the x-axis. If point object P is there, then the ray is incident on the plane refracting surface AB at Q and refracted along QR. If there is no refracting surface, actually the ray will go in straight line, that is along PQ. When we observe along the R, the image diverging from P1. So the P1 is the image of the object P. P1 is the object of the P. The object is at a distance of minus x naught and the image is at a distance of minus x1. Why it is taken as minus x naught? Because the object is at the negative x-axis. So that OP is equal to minus x naught and OP1 is equal to minus x1. And there the angle of incidence is taken as I and angle of refraction is R. Now there is two media both sides of the plane refracting surface. A left side media whose refractive index is mu1 and a right side media whose refractive index is taken as mu2. Now how can we calculate this spherical aberration? From Snell's law, we know mu1 sin I is equal to mu2 sin R. I is the angle of incidence, R is the angle of refraction, and mu1, mu2 are refractive indices of the two mediums left and right side of the plane refracting surface. When the left side medium is air whose refractive index is mu1 is equal to 1, that side, the right side refractive index may be taken as mu2 is equal to mu. So that mu is equal to sin I by sin R. In case of triangle P1QO, when you have to take tan R is equal to opposite by adjacent, that is OQ by OP1. We know OQ is equal to H and OP1 is equal to minus X1. Now we know tan R is equal to sin R by cos R. So that sin R by cos R is equal to H by minus X1. From this, X1 is equal to minus H into cos R by sin R. So in which the ray is incident at the height of H from the principal axis. That is our main aim. Because we know in paraxial rays, the H is very, very small. In marginal rays, H is very high. So let us take in this case, the ray, one single ray is incident on the plane refractive surface at a height H. Now x1 is equal to minus H into cos R by sin R. From this, we know cos R is equal to square root of 1 minus sin square R. So that x1 is equal to H into square root of 1 minus sin square R by sin R. But we know according to Snell's law, mu is equal to sin I by sin R. From this, sin R is equal to sin I by mu. When sin r value is substituted into this equation, that is x1 is equal to minus mu into h by sin I into square root of 1 minus sin square I by mu square. But from triangle OPQ, that is O, P and Q, sin I is equal to opposite by hypotenuse, that is OQ by PQ. But we know OQ is equal to H and PQ is equal to square root of H square plus X naught square. But there is hypotenuse square is equal to side square plus side square. OP square PQ square is equal to H square plus X naught square. So that sin I is equal to H by PQ is equal to H by X root of H square plus X naught square. Now that is x1 is equal to minus mu into h by h, that is when we have to substitute this value sin I into above equation, that is into equation 1, x minus mu into h by h square root of h square plus x naught square into square root of 1 minus h square by mu square into h square by x naught square h square plus x naught square, where the sign value is substituted into equation 1. So where h and cancel each other and x naught square is taken as outside, minus mu into x naught into 1 minus h square by x naught square whole to the power half, because square root that is taken as whole to the power half into 1 minus h square by mu square x naught square into 1 minus h square by x naught square whole to the power minus 1 whole to the power half. Because here also in the denominator h square plus x naught square is taken as common, so that 1 plus h square by x naught square it is taken as, that is minus 1, and square root is taken as half. According to the, when we apply binomial expansion, we know binomial expansion is x plus y whole to the power n is equal to nc0 x to the power n plus nc1 x to the power n minus 1 y plus nc2 x to the power n minus 2 y square plus and so on. When we apply 1 plus x whole to the power half is equal to 1 plus x by 2 plus and so on. The higher order terms are very small, can be neglected. So that x1 is equal to minus mu x naught into 1 plus h square by 2x naught square, because whole to the power half is converted into 1 plus x by 2, that is 1 plus h square by 2x naught square into 1 minus h square by mu square x naught square into 1 minus h square by x naught square, because 1 plus x whole to the power minus 1 is equal to, according to the binomial expansion, that is 1 minus x plus x square plus x cube and so on. The higher order terms are very small, may be neglected, so that 1 plus x whole to the power minus 1 is equal to 1 minus x. So this is the 1 minus h square by x naught square came here like that. Now x1 is equal to minus mu x naught into 1 plus h square by 2x naught square. After simplification, 1 minus h square by mu square h naught square whole to the power 4 half, where h to the power 4 is a higher order term. So that is very small, greatly small. So may we can neglect the higher order term. So that is x1 is equal to minus mu x naught into 1 plus h square by 2x naught square into 1 minus h square by 2 mu square x naught square. Again from the binomial expansion, 1 minus x whole to the power half is equal to 1 plus x by 2 plus and so on. Again higher order terms are eliminated or may be neglected. After expansion, x1 is equal to minus mu x naught into 1 plus h square by 2x naught square minus h square by 2 mu square x naught square. Again, h to the power 4 term is neglected, because that is very small word. From this, x1 is equal to minus mu x naught into 1 plus h square by 2x naught square into 1 minus 1 by mu square. So once again after expansion, x1 is equal to minus mu x naught minus h square mu by 2 mu naught 2x naught into 1 minus 1 by mu square. The image distance of marginal rays is x1 is equal to minus mu x naught minus h square mu by 2x naught into 1 minus 1 by mu square, where h is the height of the marginal ray. So that is the image distance formed at x1 is equal to this equation minus mu x naught into minus h square mu by 2x naught into 1 minus 1 by mu square. In case of paraxial rays, we know the height h is nearly equal to 0 because paraxial rays are very nearer to the principal axis. So it is taken as nearly x is equal to 0. When h is equal to 0, that is x1 is equal to minus mu x naught. So the paraxial image is x naught. This is x naught, sorry. Okay, x1, okay. That is paraxial image is x naught and image is x1. That is x1 is the marginal image. So we know the spherical aberration is nothing but the distance between marginal image and paraxial image, that is x1 minus x naught. So that x1 minus x naught is equal to this from minus this. So that mu naught x minus mu x naught plus mu x naught is cancelled each other. That is minus h square mu by 2x naught into 1 minus 1 by mu square. So this is the equation or magnitude of the spherical aberration, in which minus represents the image formed at the same side of the object. So this is the calculation or measurement of the spherical aberration. Thank you.